All right, so good morning, everybody. We're going to be doing a lesson on free body diagrams. This is basically the presentation that is on the PLTW website for the POE course, section 213 on free body diagrams. So we're going to be front-loading a lot of vocabulary and a lot of information with this unit on statics. We're spending a couple weeks on this before our break. So we're doing this lesson live, but of course I'm recording it as well for future upload to the Systems Engineering website channel, excuse me, and so you can reference it in the future. But again, students who are here may feel free to ask questions without worry of me wanting to just go straight through. I don't. All right, so let's go ahead and get started. Talk about free body diagrams. Now, a free body diagram basically is a visual representation of force and object interactions. Now, the format that PLTW uses frequently for free body diagrams are a little bit different than what you would expect in a physics class. In a physics class, typically a free body diagram consists of a box, and that box basically would have forces pointing from it, as opposed to the way these diagrams are drawn, in which case the forces are pointing to where they're being applied. So a free body diagram visually, well, most of the time, especially in physics, usually would be for a single object, whereas here you can see there's multiple objects in some cases single objects. So on the left you'll see there's a truss, and you'll be doing some trusses this next section here, and then you've got a pulley, and you also have sort of a 2x4 or beam support as examples. You'll notice that pointing to and from those diagrams, you have, what is that V word? What's the V word that we used in class before? Sorry, we're getting some sounds from my computer. What's the V word that we've used to describe things that are certain types of quantities? Remember? Vectors. Vectors, right? So these are force vectors in this case, right? So we talked about what forces are. Forces are basically something that tries to change the state of motion of something. So if it's a push or a pull, then those are considered forces. It's trying to either cause motion or stop motion anytime you're changing the state of something. So so these are all force vectors. Now, in this course, we're going to be using primarily these styles of force diagrams. We will see from time to time a traditional physics free body diagram as well. All right, let's talk about force. So we kind of already defined the force here. We have a new definition or a new interpretation of it that you can see on the board. And a force is basically a straight line, push or pull, that acts upon an object. I like to distinguish between, with the word you're going to see in a second, and a force by saying that a force attempts to translate an object. And what that means is, picture a shopping cart. If you're in the store with a shopping cart and you're going to go down the aisle and search for food, you are going to push your shopping cart by applying a force on the shopping cart handles, and of course be pushing off of your feet to get the cart in motion in the first place. That's why I always, I remember telling my 8-year-old when she's now 8, not when she was a little younger, obviously, when she was sitting in the shopping cart, and she was wondering how come she can't get the shopping cart to move. And you may want to think about that for a second when it comes to the way forces work. I am able to push the shopping cart no problem, but she is unable to push the shopping cart when she is sitting in it. So think about why that's the case. Okay, so when we get to some laws of motion, you'll kind of get the answer to that question, so if you think about it. All right, so a force is considered a vector quantity. So we've talked about vectors in the past. Vectors have direction and magnitude. They have two attributes. They have how much and where. Okay, so vector quantity, so force is a vector quantity. We need to know how strong is the force, and we need to know where is it pointing. Okay. You'll see up here on the board also, you have a vertical vector. Here's your vertical vector right here. You have a horizontal vector, and you also have an angle. You also have a vector that's at an angle. So you'll see why we have done some trigonometry work previously in the class. You'll see why we've done that now that we're now talking about forces. Okay. So remember that we've talked about vectors in the past. How long the vector is indicates magnitude, and where it's pointing indicates direction. Okay, so vectors is going to be in full, pardon the pun, in full force in this section. I know. All right, now in addition to force, we also have a concept We've talked about it in the past, but it's very important to reestablish what that means now. All right, so let's talk about now. Let's talk about the concept of moment. Okay, so you know that we can sort of push or pull something along, trying to change the state of motion. We also could cause torsion or twisting on that object. So when we try to do that, we are trying to create moment. So I'll picture, you could picture this. You know, one of my hobbies, my personal hobbies, is I like to bowl. And I like to, when I throw the ball, I not only will push the ball down the lane with my arm swing, but when I let go of the ball, I also will turn my wrist. And what that does is that creates rotation on the ball. It creates side roll. And obviously the angle of rotation can vary depending on my hand position and the way I let go of the ball, depending on what I want the ball to do. So it'll travel down the lane with that rotation, and eventually when it reaches the back end, that's when it will pick up it'll encounter more friction and then allow it to basically grab the lane and hook into the pins and increase my chances of getting a strike. Anytime you've seen, if you ever go to a bowling alley, you see somebody that's throwing the ball that way, the reason they're doing that is because it does increase the probability of getting a strike if you hit the pocket, if you hit the right spot of the pins. But I just want to obviously give you that example so you can kind of picture what a moment would be. Another example of causing moment is anytime you've opened a door. If you've opened a door, you have created moment because you are causing the door to rotate on its hinges. So when we create moment, we're just basically twisting something or causing torsion to an object. And oftentimes, interactions between objects in the universe and yourselves are usually a combination of force and moment. So sometimes, like if you, for example, push on something, but you don't push in the center of the object, you might cause both. You might cause a force, start moving, but you also may cause moment in causing it to twist. Like say, for example, if you think about the shopping cart as an example, if you push along the center of the shopping cart will move forward. But if you push on the right side of the shopping cart, you're going to cause that shopping cart to turn left. Try it next time if you're not convinced. Now with moment, we will indicate moment with kind of a vector, but you'll see it's more of an arc, okay? And the direction that it's pointing will indicate the direction of rotation. So we have a clockwise rotation and we have a counterclockwise rotation, which we'll abbreviate as CW and CCW, okay, counterclockwise. So, and again, think about a clock face. We have a clock in the room. I'm sure you have a clock in your room as well. If it's the direction that a clock is moving, that's why it's called clockwise. If it's the opposite, it's counterclockwise, okay? All right, now let's talk about the equations. And again, this is not the first time you've seen these in most cases. Let's talk about the equations. Moment is force times distance, okay? Now, the equation for moment and the equation for force are actually the same thing. The difference is the unit, A, and remember that a force that is a force is something that is applied or could be applied perpendicularly, usually to the centroid of an object, and we would note that with different units. And when we think about force times distance, I'm sorry, I made a slight mistake. When we think about force times distance, we also will consider work as involved as well. When we create or move an object along, we're using energy to do that. So everything is kind of related in this case. Okay, so moment. The D in moment is the distance, which is called the moment arm. Okay, think of a wrench. When you use a wrench, you are applying a force that is perpendicular to the side of the wrench that you are trying to rotate. So if you want to cause a counterclockwise rotation, which, by the way, would that tighten or loosen a bolt? If we do a counterclockwise rotation on a wrench. What do you think? You ever heard the phrase lefty loosey, righty tighty? Yeah? What does that mean?
If you turn it right, it'll get tighter.
Turn it right, it'll get tighter. Turn it left, it'll get looser, right? So that's typically a counterclockwise rotation to loosen it. So in this case, you could think, well, where's the rotation point, the axis, and what direction is the force pointing relative to that axis? So in this case, this wrench is going to move counterclockwise. Okay, here's that point of rotation, and here's that line of action. Right? So what's going to happen here is you're going to get, and there's that distance, by the way. There's that distance right there. Okay? And what happens here is you're going to end up getting a counterclockwise rotation. Now, if you increase the distance, do you get more or less moment? If you make, let's say if you make that wrench longer, do you get more or less moment?
More.
You get more, right? Distance is directly proportional to moment, right? The longer the arm, the longer the lever arm, the longer the moment arm, the greater the moment. So you could use the exact same force and get a longer wrench, and you will create more moment. Okay, you of course also can apply more force to do the same thing, or a combination of the two, to get the same thing accomplished. Okay. Questions on that? Any questions on that concept? All right. If you're watching this video and you have questions, you can of course add your question to the comment section below. All right, let's talk about another example. Okay. Let's say we have some textbooks. You don't have to write this in your notes. Let's say you have a stack of textbooks, DE, POE, IED, PLTW books, right? Okay. They each weigh 5 pounds and they're sitting on top of a table. What is the free body, or what would the free body diagram of the top book be? All right. So here's a question for you. Okay. What kind of forces are applied in or on the top book? All right. What kind of force is being applied to the top book? Let's think about that for a second. Go ahead. What is it? The weight of the book, right? The weight is a force, right? Weight's a force. What direction would weight point? Down, right? Towards the center of the earth. So if we start with the isolated object, which in this case is the top book, here's the top book, okay? And then we think about the forces that are applied to it. So there's actually not just the weight, but there's another force that we also can indicate as well. Now, I like to kind of give this example with your understanding what this force is. The book is resting, right? The book is not moving. If this was the only force applied to the book right now, what would happen? If that's the only force on that book, what would happen?
It would slide off.
Would it slide off?
I think that it would just sit on the table because gravity applies the force.
Okay.
Oh, if it's just.
If it's the only, if the weight of the object is the only thing holding it or happening to it, right? Right. If the weight is the only object, force. You hear that? Yeah. That's a textbook falling to the ground. That was a textbook that had a force, had the weight only applied to it just for a couple of seconds, right? Or less than a second. Okay? So right now it's on the table. Why is it not falling to the ground? The table is supporting it, right? Yeah. In that diagram, is the table supporting it directly?
Yes. No, the two books.
Yeah, the two books below are, well, really the one book, right? The one book below is supporting it. So we call that's called a reaction force, first off, right? It's basically the weight of the book, which is 5 pounds in this example, is being supported by a 5-pound opposite force, which we call the normal force, okay? We don't want to say, we don't call it the, it's not normal because we don't call it normal because it's weird or anything like that. It's just the normal force, okay? It's a reaction force to the weight of an object. Right now, every single one of you has a normal force being applied to you, okay? For me, there's a normal force applied to me from the floor because I'm standing on it. For you guys, there's a normal force from is it the floor? Directly? No, the chair, right? You're sitting in it, right? So if you're watching this video while you sit, your normal force being applied from the chair. So whatever you weigh, the chair is supporting you in the equal and opposite direction to keep you from falling, right? Now, if you like to tilt your chair backwards, what if the centroid of you and the centroid of the chair kind of overlap and compensate a little bit, then you'll fall backwards. Of course, you don't want that. All right, so objects and forces, right? Here's the deal. So we have a weight of 5 pounds, and we have a normal force of 5 pounds. I like, personally, to label these as F sub W and F sub N, okay? I actually prefer to label them with F's and subscripts as opposed to just these, because these can get a little confusing. So you may notice that they'll do this in some cases. More complex free body diagrams, like the ones you'll see, here's an example of one you'll see for trusses. Okay, more complex free body diagrams will have more forces, more dimensions, and also some angles that are thrown in as well. So as you can see, they can get very simple, like in this example with the book, but they also can get very complex. And in this case, they will get complex pretty quick. All right. So I'm just going to skip a couple of slides. There is another example of a free body diagram here, and I'm going to go ahead and just move to the more intense content and just for now. All right, so let's talk about this example right here. A person pushing a fridge up a ramp. Okay, if we think about a free body diagram for this, let's see if we can figure out how many forces are being applied on this fridge right now. If you think you know one of the forces in the diagram, go ahead and call it out.
The ramp.
Okay, what about the ramp?
The slope that it has, by like the way that I think it's easy.
It's like easier than like lifting it, right?
Well, pushing it up the ramp, yeah, there's definite mechanical advantage because we're using an inclined plane, right? He has an easier time pushing that fridge up the ramp for that reason. That's true. But the ramp is applying a force to the fridge. What would we label that as? It's not a weird force. It's a normal. It's a normal force, right? Yeah. All right. Oh, yeah. No, not a weird force, right? So there is a force being applied from the ramp. It's the normal force, but is the normal force pointing directly upward? Is the normal force pointing directly upward? What do you think? How about what if he lets go? What if he moves away? Will the fridge move?
Yeah.
Yeah, the fridge is going to move, right? It might topple, it might slide, right? But it's going to move because the force that the ramp is applying is actually going to be kind of at an angle. Okay, it's going to be kind of at an angle. Let's kind of go through this here and see, right? There we go. Here's our fridge. There's our box to represent. There's the weight of the fridge. Weight still points downward no matter what. The weight is always going to still point downward. But notice now that the normal force is applied at an angle because the ramp is on an angle. So the angle of that ramp will also be the angle on the vertical of the normal force, which is why, like I said, if the guy goes away, that fridge is going to start sliding down the ramp. It's certainly not going to slide up the ramp. Now here's your applied force, also on an angle, right? And there's also a force of friction involved. Because because no things in the world are truly frictionless. There are things that are very easy to slide over, like ice and Teflon, right? But there's also things that have more significant force of friction, like carpet. Okay. This ramp is most likely not made of carpet. Okay, so there's that. And notice, of course, there's 4 forces in the problem. There is an angle of incidence, so those angles do matter. Okay. For this video, I'm going to skip the pulleys because we do a lot more. We do a lot more with translational forces in this example. So we're going to skip this. Okay. So we're going to talk now about free body diagram reactions. All right. Now this is very important, especially when we get to the trusses. This is a very important concept to understand. When we stand on a floor, or we sit on a chair, or we put things on a table, it's very easy to determine the reaction forces, okay? They basically would point opposite the weight. If you're standing on a level surface, it'd be opposite the weight. If you're standing on an inclined surface, it would point at that incline away from you, okay? So that's why, like, if you put a ball on a sloped surface, the ball will roll down the sloped surface because its normal force is being applied on that angle. Now, there are 3 types of support reactions that we're going to talk about in this part here, okay? We're going to talk about cables, ropes, and chains. Think of them as one different object. A cable does apply a reaction force when you think about, like, if you tie something to a rope or you hang something from like a picture wire or something like that. Those do apply a reaction force. There's also a pin, like if you pin the weight stack in the weight room. Okay, that's an example. And there's also what's called a roller. Trying to think of a good example that you could think of for a roller. I would say, a skateboard. Okay, a skateboard. Good, the wheels on a skateboard. And there's also something called a cantilever, or built-in end. The best example of that is if you've ever seen a signpost hanging outside of a store that's hanging over the sidewalk as opposed to up flush against the wall. That's an example of a built-in end or a cantilever. Another example of that is if you have a patio that has no underlying supports on your house. Like if you have a patio that's just kind of like it sticks out from the building and then there doesn't look like there's anything obvious supporting it. Chances are there's a couple of I-beams that are in and underneath your house to help support that. That's a cantilever support. All right, so with free body diagrams, it's very important, like I said, to identify these reaction forces and what kinds of reaction forces you would get from them. All right? Connections are often identified with letters, and we'll talk about that in just a second. Now, let's start with cables. Cables, ropes, chains, anything that's sort of corded, you get a tension force when you use that for support. And here's an example of that. A rope doesn't support anything until it is fully extended. Okay? So like if you think about like a tug of war rope, right? You pull on the rope and the rope is not tied to anything, you're not gonna, there's no resistance whatsoever to that. However, if one of the other ends of the rope is tied to something and you pull, once you reach that maximum length, that's when you start to feel the resistance. Okay? So a cable or rope or chain is only going to have a tension applied to it. So let's say we had a weight hanging from the ceiling, right? If that weight's hanging from the ceiling, we get a tension force that is equal and opposite to the weight of the object. Makes sense. If it's a 10-pound weight, you're going to get a 10-pound tension force on that cable. And if that cable is rated for less tension, what's going to happen to the cable? Let's say the cable only is supposed to hold 5 pounds, and you hang a 10-pound weight on it. What's going to happen to the cable? It's going to snap, right? It's the tension force is going to be too much for it. So, you know, that's something, right? So you get a tension from a cable. That's nice and easy. There's your tension force. In this example, if we hang a sign, and when we got 2 cables to support it, where would the forces point? Just like that, away. Okay? So when you have a tension force, another kind of good idea here is when you have a tension force, the tension is going to point away from the object that's causing it. It's causing the tension. Okay? Now, if you have a pin support, like this, the symbol, note the symbol for a pin support. You got a little triangle with a horizontal line underneath it. I'll point to that so you can make sure you understand right here. That's the symbol for a pin support. When you have a pin support, you are getting support from 2 directions. You are getting a vertical, and you're also getting a horizontal support. Okay? Perfect example of something that uses a pin support is a bridge. At one end of the bridge, you're going to have a pin reaction force to help support, or pin connection, I should say, to help support the truss and support the span. All right, so you get 2 forces. You get 1 vertical, you get 1 horizontal. We would label those, note the label here. If we say that that's point A, R sub AX, that means reaction on point A in the X direction. Reaction on point A in the X direction. What do you think we're going to label the other one with? Ooh. What do you think we're going to label the other one with? Is that other label, that other force that's pointing upward, is that a reaction force? Nod your heads. Yes, it is. It is a reaction force. What point is it at? It's also at point A. What direction is it in? Well, what do we label the vertical direction with? With a vertical, right? So it's a Y. So there's a reaction force, joint pin A, X direction. Then we have R sub A sub Y, which is a reaction force on point A or joint A in the Y direction. Okay? So a pin support will have both RAX or RX and RY, reaction in the X and a reaction in the Y. Now, a roller support is different than a pin support in one very specific, still very important way. First off, understand, again, I use the example of a skateboard. A skateboard can roll horizontally, but it will still support the rider vertically, right, when they stand on it. So they can still move horizontally. And also, when it comes to truss designs and bridge designs, a roller support allows the bridge to expand when it undergoes thermal expansion. You understand, of course, that when you heat objects, they get bigger, right? When you heat up objects, they get bigger, and obviously how much bigger depends on what it's made out of. But a bridge is no different, right? If you don't allow a bridge to thermally expand when it gets warm outside, it will buckle and crack. So on one end of the bridge, or at some points of the support along the span, there's these roller connections that will help support the span horizontally, but will also allow it to expand horizontally without, being pinned in place. So we call that, as I said, a roller connection. Note that the symbol for a roller connection is similar, but we use a circle to indicate that it's a roller connection. The thing, if you think about the skateboard, you can picture that this beam can glide along that, right? Glide along horizontally. A roller support will support the load in one direction. Usually, and I should say usually, that direction is going to be perpendicular to the roller support. So if you see that roller support is horizontal, like this, then that's going to provide a vertical force, vertical support force. Okay? So again, the labeling would be the same. This time we have a reaction force. It's vertical. It's on point A. So how would we label this? Well, we would label it the same way. R, reaction force, on point A in the Y direction. So if you have a free body diagram where there is a vertical support, a roller support, it would get a vertical reaction force. And as I said, these will be very important once we get talking about trusses and beams. Okay? All right. Now let's use an example that we've talked about or we've done in the past. Okay? This class's last marking period did beam deflection. And in our case, we used textbooks as the supports. Okay? Those textbooks were more of a roller support than they were a pin support. But because they were flat, they had a good amount of friction, they did kind of pin the beam in place, but do still allow it to move and deflect. Okay? Beams and truss bridges are usually supported with one end being pinned and another one on a roller support. We call this a simply supported object. All right? That again would allow for thermal expansion and or compression along the bridge. All right, so we have an example here. This is your beam deflection example. You stood in the middle, and the beam would deflect. It will also allow it to compress. It would also allow it to create tension on certain spots, et cetera, et cetera. But that free body diagram would be very, very easy to make. Now watch this. You see how we had a load in the middle? Well, that load in the middle is a force on the beam, right? Okay? Kind of looks like a lever. Right? When you look at it from the side, look at our 2x4, it did kind of look like a lever. You're right. So let's go ahead and create a free body diagram of this. What's one of the forces that is on the beam? What's one of the forces that is on the beam? Gravity. The weight of the beam is definitely a force. Okay, the weight of the beam, but also the weight of somebody who's standing on it too, right? So we could call that, right? Oh, sorry, back up a little bit. Previous. Okay. We can call that the weight. We can call that FW. We can call it the weight of the person, or the weight of the beam, or the weight of the beam and the person, right? All of those are possible. In our context, we most of the time will ignore the weight of the beam itself and just focus on the loads. Now, this load is on the beam, pointing in the vertical direction. What kind of support is at point A? Is it a pin or a roller? Pin or a roller at point A? That's a pin, right? How many reaction force or forces are on the pin connection? What are the reaction forces at the pin connection? There's less than 4. There's less than 4, just 2, right? There are 2, and they're pointing in both horizontal and vertical directions, so we can kind of get that in there too, right? Here's our RAX, here's our RAY. Now on the other end, we've also got a roller support. how many forces would be reacting at a roller support? At a roller support, how many forces are there? The answer is just one. In this case, the roller support is horizontal, so we get a vertical reaction force. Now, quick question for you. Let's suppose the person standing there, let's say that weight vector is a person that weighs 250 pounds. Okay? So he's 250 pounds. This force right here is 250 pounds. Right here. Where's my mouse? Where's my mouse? There it is. Right here. That person's 250 pounds, right? And he's standing he or she is standing in the middle, right, of the support. So there's no side to side. You know, it's on the centroid. You get maximum deflection at that point, right? How much force would we get at the pin and at the roller supports? How much weight do you think is on both of those spots? He or she weighs 250 pounds, right? Keep losing my mouse. There it is. 250 pounds right here. Is there 250 pounds right here?
No.
Is there 250 pounds right here? No? How about 125 here?
Yeah.
How about 125 here?
Yeah.
Yeah, that makes sense, right? If the person moves over here more, so maybe where my mouse is right now, more or less weight at R-A-Y?
More.
More. More or less weight at R-B-Y?
Less.
Less. Good. Okay, so you have a good grasp of that as well. Okay, one more for your notes, and that's the cantilever support. So we talked about having a possible with that as well. A cantilever is a combination, I think of it as a combination of a pin connection, but at the same time it will also cause or attempt to cause moment. Okay, so you get a horizontal and you get a vertical, but you also will get a moment. Okay, so here's your RAX, here's your RAY. You will also have a moment that's created, which makes sense. If you think of this as if someone's standing on this spot, what wants to happen here is you want that point A wants to rotate, okay? Because you're applying a moment on that lever arm. So the reaction there would be to try to keep it to be fixed in position, and then you would get a reaction force on the object, okay? So that right there is pretty much your presentation on reaction forces and free body diagrams all at the same time. Okay, so I hope you enjoyed it. I hope that if you made it this long, I hope that you go ahead and click like on this video if this helped you understand reaction forces and free body diagrams in any way. If some of the examples hit home for you, I would really appreciate, again, if you would subscribe and like this video. Have a wonderful day, and don't forget to be awesome.